Welcome to the NHERI SimCenter's Live Expert Tips. In this session, we will introduce you to the uncertainty quantification concept of random fields for correlations of spatially distributed assets in the context of fragilities for regional seismic analysis. Our expert today is Sebin Oh. Sebin, thank you for being here. He is a PhD student in civil and environmental engineering at UC Berkeley, where he develops a unified framework to analyze regional seismic behaviors at different scales by introducing concepts from statistical mechanics. His research interests include reliable structural modeling, surrogate modeling, Bayesian updating and inference, and probability-based regional analysis under natural hazards. Sebin, thank you for being here, and we invite you to begin.
Right. Yeah, thanks for the introduction, and thanks a lot for having me. So today, I'm gonna talk about fragility field for the regional performance-based earthquake engineering, PBEE in short, using the R2D tool. And this is still an ongoing project, ongoing study. So I'd be very glad to hear your comments. Yeah, so the PBEE framework is the framework that focuses not only on the reliability of a structure, but also on the practical quantities that are important for decision making, such as repair costs or serviceability. So it has been widely developed and implemented originally for a single structure, and recently several research efforts have been made to extend this approach to a regional scale. And to apply this PBEE framework at a regional scale, first identify, let me move it to major point. Yeah, first identify the region, the domain of interest. Then we simulate the ground motions over the target region and evaluate the damage states or performance states of the target region. Finally, some decision-making metrics are calculated based on the estimated response here. And the part I'm going to talk about today is about this part. So given ground motions, how can we simulate the regional responses? And by regional responses, I mean the damage states of all structures in a region. So roughly speaking, the approaches for simulating the damage state of structures in a region can be divided into two approaches. First one is physics-based simulations. In this approach, the damage state of structures is computed using detailed structural models and nonlinear dynamics. It may accurately simulate estimated structural responses over a region, but it requires significantly large computational costs in general. And because it is too heavy to run multiple times, it's difficult to extract probabilistic descriptions, which are typically very useful for decision making. So alternatively, we can use stochastic simulators to simulate the regional responses under an earthquake. Here, stochastic simulators are nothing but the joint probability distribution of the damage states of structures in a region. In other words, if we know the probabilities of any configuration of a region, then we can generate samples about the regional response given the hazard scenario. So this approach is computationally much more feasible, but it depends highly on which assumptions you made to the statistical models. And what I'm going to talk about today is about this second approach. And The most typical stochastic simulator used for simulating the responses of a single individual structure is the fragility curve or fragility function. The fragility function is assumed to follow a log normal distribution as shown in this right figure. So when the intensity measure of a ground motion is given, such as peak ground acceleration PGA or spectral acceleration SA, when those are given, the fragility curve gives the failure probability of the structure. And you can generate samples of the response of the structure by following the failure probability given by this fragility function. And this is, note that this is just for a single structure. Then how can we get the probability for a group of structures? We have fragility curves for individual structures in a region, which means that we have marginal distributions, marginal probability distributions like this. But what we need is a joint probability distribution like this. And this joint distribution is different from just a collection of marginal distributions. Those are different. So we need to integrate the current knowledge to have a joint probability distribution distribution for the structures in a region. And currently, some artificial assumptions such as independence or equicorrelation assumptions are typically made, but it can lead to like a significant underestimation of the system level regional risk. And just as the marginal probability distribution is called the fragility curve, I call this joint probability distribution a fragility field. Maybe fragility surface would be more intuitive, but I just stick with the term field because the term field is more common like expression in the field of uncertainty quantification. And I introduced the Ising model from statistical physics as a very promising model for the fragility field. This model was originally developed to explain ferromagnetism in physics, but from a statistical point of view, this is nothing but a joint distribution having a maximum entropy for binary variables when this information is given. Then what does maximum entropy means, and what is the advantages of a probability distribution having a maximum entropy? In information theory, the entropy is somewhat related to the information. So the probability distribution having a maximum entropy means that it keeps maximum information, maximum amount of information while transforming the given knowledge into a model. So if we introduce any artificial assumptions like independence or Gaussian assumptions, the resulting distribution will have lower entropy, meaning that some information is lost. In this sense, the maximum entropy model is sometimes called least structured model. So in other words, if we know the failure probability for each structure in a region and correlations between them, the Ising model is the least structured model, describing the target region. And I'll explain the meaning of each parameter and variable in this model in the following slide. Yeah, so here the Ising model in the Ising model, P large x equal x means the probability for the region to have the configuration x, and here X means the damage state of all structures in the region. And damage state or performance state of ith structure is represented as xi, where xi can only have binary values. So +1 for, I just used +1 for failure and -1 for safe. And z is just a constant that normalizes the sum of all possibilities to be 1. And here n is the number of structures, which is equivalent to the scale of a region. And the most interesting part is this H and J. So if you look at this equation, if Hi is positive, then the probability of Xi is +1 is larger than it is -1. Which means that the ith structure is likely to fail, and vice versa for negative sign. And also this tendency gets stronger as the absolute value of Hi gets larger. So therefore, in this sense, Hi is interpreted as a risk field acting at the ith structure. So when Hi is positive, here, Xi to be +1 is more likely to occur than Xi is -1. Yeah. Similarly, if Hij is positive, Xi here Hij is positive, Xi and Xj are likely to have the same sign, meaning that same states. And it means the ith and jth structures tend to have the same state, and vice versa for the negative sign, of course. So in this sense, Jij is interpreted as a pairwise interaction between ith and jth structures. So when Jij is positive, Xi and Xj tend to have the same sign here. Okay, so now let's take a look at how to construct the Ising model, and by extension, how to construct the fragility field. As I said earlier, the first and the second order moments are the only ingredients, the only information to construct the Ising model. And in the context of regional seismic analysis, you can just understand the first order moment as the failure probability of each structure, and this second order moment as correlation between the failure events of each structure pair. So for the target region under a given hazard scenario, you obtain the first and second order moments. And then we can construct the Ising model by estimating the parameters that will produce the given information, these two. And this Ising model is the joint probability distribution for the target region only under the given earthquake scenario. And by iterating this process over different hazard earthquake scenarios, we can finally get the fragility field that is the joint probability distribution for the target region. And it takes the hazard scenario as an input and gives you the probability of each possible configuration of a region. Then, yeah, how can we get this information about the first and second order moments, which are the only information needed? Well, there are many different ways to get this information, but I'm just going to focus on the use of R2D tool here. For the target region, you can generate samples using the R2D tool under the given specific earthquake scenario. And I generated 10,000 samples. And then you can just compute the first and second order moments from the generated samples. And finally, you can just construct the Ising model like this by estimating the parameters from these two information. Let me show how it really works. The target region is a small neighborhood in San Francisco, which consists of 182 buildings. And for the earthquake scenario, the epicenter is shown in this figure like this, and a magnitude of 7.0 is assumed. And using the R2D tool, a total of 10,000 samples was generated for this region. And these figures show the simulation results of the R2D tool. This left figure shows the failure probability of each building, and this right figure illustrates the correlation coefficient for each building pair. And now that we have the first and the second order moments, we can now construct the Ising model using this information. So using the obtained information, estimate the Ising model parameters H and J. And once you estimate these parameters, the Ising model construction is done. And to see if the model was well constructed or not, I used the Markov chain Monte Carlo sampling technique to generate samples following the constructed Ising model here. And these two plots show how well the Ising model was constructed. And in both figures, x-axis are the given statistics, and given statistics that are obtained from the R2D, and the y-axis are the reproduced statistics using the constructed Ising model. And the points in both figures are distributed along the identity line, meaning that the constructed Ising model successfully reproduces the given information. Yeah, but note that this Ising model describes the target region only under the specific given hazard scenario, and it is not a general model for the region. And fragility fields should not be limited to a specific scenario. So to obtain a fragility field for the target region, technically we need to construct the Ising models for various earthquake scenarios. But the problem is the parameter estimation procedure takes too long time to consider a sufficiently large number of scenarios. So currently, the direct relationships between the Ising model parameters, H and J, and the given information, first and second order moments, are being explored. So to sum up, first, I have talked about the need for the development of a fragility field is necessary. It's necessary for the regional PBE framework, where currently unrealistic assumptions are being made. And just like when we apply the PBE framework for individual structures, regional PBE requires a stochastic simulator that provides probabilities for the regional responses for a given hazard scenario. And to this end, we are exploring the Ising model as a promising interpretable model for the fragility field. But first, this model is maximum entropy distribution, which means that it is the least structured model without any artificial assumption while accurately reproducing the given information. Second, the Ising model is constructed purely on data. It doesn't matter where and how the information comes from, as long as you can get the first and second order moments. And today I just showed you the examples based on the R2D tool, but the Ising model can also be constructed from the post-earthquake field investigation, where the Ising model-based framework can provide more benefits than in the R2D example. And last, the parameters in the Ising model have clear physical meaning. And today I couldn't have time to talk enough about the interpretation of Ising model parameters and their implication into understanding of the regional seismic responses. But investigating the estimated H and J values for a target region under different earthquake scenarios can provide deeper understanding about the regional seismic responses. And also, since the Ising model is the very fundamental model in statistical physics to study more advanced, like multi-scale behaviors of a complex system, we are trying to apply more advanced concepts in statistical physics to deeply understand the collective and multi-scale behavior of regional seismic responses. And yeah, if you're interested, you may check out this paper here. Yeah, thanks for listening. And this pretty much of it. Yeah, thank you.
Sebin, thank you very much for the presentation. We have a couple questions from the audience, but that was very informative. So I think the first question is, in the Ising model, you had you had a plus or a minus X, which was failure or safe. Does that mean complete collapse of the structure? Or are there intermediate limit states that can be considered in this framework?
Yeah, so it depends. I mean, it depends on the limit states. Yeah, so if you define your limit state as the collapse or failure event of a structure, then this failure means the complete collapse of a structure, and the safe means non-collapse event of a structure. But if you just define your limit state as like based on the serviceability or some like third damage states, then the definition of this failure can vary.
Okay.
Yeah.
So it's not a collapse failure. It's simply a term you're using to define the particular state that you're considering.
Exact.
Okay. If you want to consider correlated damage in a region, you could choose from some other classical probability models like a joint log normal. What was your motivation or maybe the advantage of choosing the Ising model over maybe a more traditional probability model?
Yeah, so yeah, that's really good question. So the classical approach using the joint normal distribution, I mean, I feel like there is no reasonable or like plausible reason for using the Gaussian assumption, because the fragility curve was just assumed to follow a log normal distribution, and based on this fragility curve, people wanted to construct the joint distribution, and the easiest way is to just assume the joint distribution is the Gaussian. So I feel like there is a research gap between them. And then the most attractive point of this Ising model is it doesn't rely on any artificial assumption. It's just the result of purely the maximum entropy principle. And that is the first attractive point of this Ising model. And the second point is it has clear physical meaning like this. If you use the joint normal distribution, each parameter are just mean and covariance matrix. There are no like those have their statistical meaning, but they cannot be used when you want to interpret or when you want to deeply understand the original response itself. But if you use this Ising model, because this H and J have their own physical meaning, you can understand what's going on in this region by looking at the change of H and J values.
Okay. There are a couple other questions coming in. In the Ising model, the J matrix is the correlation matrix. How did you learn the correlated coefficients? Is this from real-world damage data, or specifically, where did you obtain the correlation?
Yeah, so in this example, in this R2D based example, I just followed the default setting of the R2D tool. I mean, they, okay, let's go in this. Okay, let's just stick to this example. I assumed earthquake scenario like this, and then inside of the R2D tool, they generated ground motions over this region using some the ground motion prediction equation or something like that kind of stuff. And then based on the ground motion in the R2D tool, they estimate the damage states of each building using fragility curve, using individual fragility curve. So this results from R2D tool or cannot be said the realistic realization of like regional response, because it just relies on the use of the fragility marginal individual fragility curves. So the reason I said in the conclusion that the Ising model-based framework could be more beneficial when you rely on the post-hazard field investigation data. In that case, if there is no information about any like fragility curve or correlation about them, you can just use the field data. So after like earthquake, you just observe which building has collapsed or not. And then using that observation data, you can just construct the Ising model from even for that single data set. So
Right.
yeah, okay.
So you could have used observational data. You didn't have observational data, so you created simulated data using the R2D tool for this subset. With 182 buildings, does the Ising model scale beyond your, let's say, very localized region of interest here with 182 buildings to a much larger region? Or is there a practical limit to its application to a regional simulation?
Yeah, that's a very good question. So the parameter estimation task for this Ising model is kind of the computational bottleneck. So around for now, around 200 buildings, it's my best. I mean, using my computational resources, beyond like several hundreds or beyond like 1,000 number of buildings, it's currently impossible to estimate the parameters of the Ising model for that kind of large region. But so I'm trying to apply the parallel computing technique for this approach, which can like size up or scale this framework up a lot. Yeah, but currently, yeah, around 200 or like 300 at maximum. It's the current limitation of this approach.
Okay. And there's a question about the R2D tool generating correlated damage states. Which model does it use for that? And I think the question is, which model is being used for correlated damage states? And I think the answer is that it currently is not, which is why you're creating this, using this Ising model. Is that correct?
No, I mean, the R2D results from the R2D tool contain correlation between the collapse events because they didn't use correlation between the capacity of each building, but they did use the correlation between the ground motions. So which lead to the correlation, correlation between the final response of structures. So as you can see here, the failure collapse events of each structure have like this kind of correlation structure. These are purely from the R2D tool. And this correlation is from the correlation of ground motions, not from the correlations between the capacity of structures.
Okay. Why should we use this fragility field instead of using data of the fragility curves directly in our performance-based earthquake engineering assessments?
So the question is why we should use fragility field instead of just using the collection of individual fragility curves.
Correct.
Because when you use individual fragility curves to generate the samples for each building, you're implicitly assuming the independence. Those are independent because but so the correct, accurate approach is to generate samples together, not one by one. To generate samples together, you definitely need a joint distribution, which is fragility fields.
Okay. Your fragility field is coming up with the probability of failure, or
Yeah.
correct?
So when you for the given like when you look at this fragility curve, it takes the intensity measure, which can be seen as like earthquake scenario. It takes earthquake scenario as input and it outputs the probability of like failure. So just like that, in the Ising model and in the fragility field, it takes the earthquake scenario and it will give you the probability of each configuration of a region. And by configuration, I mean the response of a region. So if first building has collapsed and second is not, third is collapsed, then it will be -1, +1, -1. And the Ising model and fragility field will give you the probability of that configuration. And because you can just input any configuration in this equation, you can have kind of complete description of the target region in terms of probability.
Okay.
Yeah, that is the basic like concept of fragility field. Yeah, but I know it's a bit confusing, but yeah.
Okay, well, I really appreciate you taking the time to answer these questions. Thank you to the attendees for your questions. I think this was a really interesting use of some uncertainty quantification methods that are new to a lot of us. So thank you for sharing them. Thank you to the attendees, and I want to remind our online viewers that you can sign up for additional live webinars and other events on our webpage, which is simcenter.designsafe-ci.org. This concludes today's live expert tips with the NHERI SimCenter. We hope you've been inspired by this research and see opportunities for adapting or expanding the capabilities to your own work. Thank you very much, Sebin.
Thank you so much.